As an example, let's say you are at the top of the building and you have a bowling ball with mass, let's say 8 kilograms. And you're going to drop this onto a spring. And let's say the spring is at rest. Let's say the spring is 3 meters long. And of course, we'll also want to know how high the bowling ball is to start with. Let's say the bowling ball starts off, and let's say 12 meters off the ground. And we're going to drop it onto this 3-meter spring mounted on the ground. And what other information do you think we're going to need to know about the situation?
The K value for the spring?
Yeah, we're going to want to know K, the spring constant, because that tells us how sturdy the spring is. So let's say we also know that. Let's say we know that the spring constant is, let's say, maybe 400 joules per square meter. And let's say we drop the ball from rest. And let's say it lands on the spring, and we want to know how much does it compress the spring? Because presumably when it's going to get faster and faster and faster, hit the spring, compress the spring, slow down, come to a stop. And let's say we want to know how much does the spring get compressed. Or an alternatively, we could ask that is just what's the final height of the ball? Or what height, in terms of how far off the ground, does the ball come to a stop? And afterwards, it might be the case that maybe the ball hits the spring, compresses the spring, comes to a stop, and then bounces back up. We don't care about that though. We're just looking at how much does it compress the spring? What's the final height of the ball at the instant it comes to a stop? Any questions on the setup of that so far? So if we want to compare, presumably we want to compare initial and final values. Maybe initial value, I guess, would just be the instant we let go. What would be a good final situation to consider?
The moment the ball stops moving.
So the final situation, if we sketched out just the spring and the ball, presumably the spring is somewhat compressed and the ball has come to a stop. So the final height is unknown. I guess we could call 12 meters y initial. Final height is unknown. Final speed is presumably 0. It has come to a complete stop. And final compression of the spring is also unknown, because we're going to want to care about how much the spring is compressed.
I have a question.
Yeah, go ahead.
So how do you know that it doesn't compress the spring and come back up and where that energy goes?
Realistically, it probably does. After this, presumably the now compressed spring is going to push back up, because a compressed spring is going to exert a repulsive force. So the ball is going to bounce back up. Maybe not all the way back up. Presumably it's going to lose some energy. But we don't really care how much it bounces back. What we want to know in this particular situation is how close does it get to the ground? What's the height at the instant it comes to a stop?
Okay, so when velocity is 0. Okay,
Right.
I see.
And of course, more stuff is going to happen after that. But what we're considering here is how close does it get to the ground? What height does the ball come to a stop? Regardless of what might or might not happen afterwards.
So would that mean that there's no change in kinetic energy since we're only looking at the initial and final positions?
Exactly, and that's a very good thing to look for. The fact that the initial speed, because we dropped it from rest, the initial speed is 0. The final speed, since we're looking at an instant when it comes to a stop and is presumably about to turn around, is also 0. So the fact that initial and final speeds are the same means kinetic energy does not change overall. And of course, there's changes during the process. It's getting faster and faster and faster. and then slower and slower and comes to a stop. But the initial and final values are the same, so we don't have to worry about the overall change. Delta kinetic energy only cares about initial and final values. If we did want to consider what's going on in between, we could try drawing out a graph of the energy versus height as well. And that can be useful for other reasons. But if all we care about is the final situation, we can ignore what happens in between. On that note, what types of energy are changing?
Potential energy of gravity.
Yeah, we definitely have a gravitational potential energy because the ball height is changing.
Then potential energy spring mass.
Right. We've also got this potential energy of the spring changing because we're changing the effective length of the spring. We're displacing it from equilibrium. For gravity, would you say potential energy of gravity has increased or decreased?
Decreased because height decreased.
Exactly. Height is the indicator. The height of the ball has decreased. In fact, we can even list out, well, we can list out the initial value. We don't know the final value, but we can just leave that as an unknown variable. And what about spring potential energy?
Would you use both spring potential energy and gravitational potential energy?
Yeah, because they are both changing. From initial to final, the ball is changing height, and also the spring is changing its length.
Oh, I see. So is that just because the mass isn't connected to the spring? Like if the spring extended the entire length of the, 12 meters, then you wouldn't have to include the potential gravitational because...
There are two ways you could do it. One way is you could certainly just use potential energy of gravity for the ball and separately potential energy of the spring. The alternate approach where you're using the potential energy of the spring mass system overall is a way you can ignore gravity by instead looking at the new equilibrium length of the spring. And with the mass attached to it, the spring has a new different equilibrium.
Okay, that makes sense. Thank you. I think that's what we looked at in lecture or something like that, which is why I had it in my head.
Yeah, and that is often useful for dealing with if you've got a mass that's permanently connected to a spring and it's oscillating. That can be a useful way of simplifying the situation by ignoring gravity.
Okay, thank you.
It's never necessary though. You can always analyze the situation by looking at potential energy of gravity and potential energy of the spring, ignoring the mass attached to it, just using the original true equilibrium. But using the modified equilibrium is a very clever way of getting away with ignoring potential energy of gravity if you're looking at oscillations. But in this case, I think it would be more convenient to consider both of them because the ball is definitely changing height. And also, if you wanted to use the spring mass combined potential energy system, you basically have to split this up into the period of time when it's not attached to the spring, and then separately the period of time when it is attached to the spring. And I think that would make it even more inconvenient. So in this case, I would just treat potential energy of gravity changing because the ball is changing its height, and potential energy of the spring is changing because the spring is changing its length. In fact, we can even list out some initial and final values. If we treat X as how far the spring is compressed, at the very beginning, how far is the spring stretched or compressed?
0.
Yeah, there's no stretching or compressing at all. And then for the final situation, that's also unknown. We don't know how much the spring gets compressed. But we know it's getting compressed. Regardless of whether we treat X final as positive or negative, what's happening to potential energy of the spring?
Increasing.
Yeah, if you move away from equilibrium, regardless of whether you take the spring at equilibrium and compress it, or take the spring at equilibrium and stretch it, in both cases, you're doing work to increase the potential energy. So we usually use, sorry, what was that?
Also, isn't it a closed system? So potential energy of the spring mass would have to be positive.
Yeah, that's another sign we can look for. The fact that in this case, we've only got two types of energy changing, and we're assuming it's a closed system. So if one of them decreases, the other one has to increase. But we can also look at that in terms of the indicator. For potential energy of the spring, because the X is squared in the formula, sign doesn't matter. So we treat absolute value of X, the displacement, as the indicator variable. It is getting further from equilibrium. So absolute value of X is increasing, meaning that's an increase in spring potential energy. And as you said, we're going to be treating this as a closed system. What would be some possible ways this could be an open system? How could this possibly be losing or gaining energy?
Like air friction?
Yeah, if you got say if you have to consider the air, if there's air resistance, if the air is thick enough or the bowling ball is spread out enough that you have to consider the air it's pushing out of the way. But a bowling ball is pretty dense and compact, and it's not traveling at a tremendously fast speed. So I would assume air resistance can be ignored here. Which means these changes have to add up to 0 because it's a closed system. And we should be able to fill in some formulas here. What's our usual formula for potential energy of gravity?
mgy.
Yeah, and since we're looking at a change, we will include the mg delta y.
I just have a clarifying question about the spring energy. So you would do the like x initial and x final. Is that all in relation to the equilibrium, not necessarily equal to the ground?
Yeah. Yeah, so x represents how far the end of the spring is from equilibrium. So
okay.
if you have certain, presumably the spring is, the location of the end of the spring when nothing's attached to it is equilibrium. So this location is what we're calling x equals 0. This height we're still calling x equals 0. It's just that the spring is now in a different location. So that means its final x value is non-zero.
And then would the final height and the like y final and x final be the same? Like would those equal each other?
Not quite. They're definitely going to be related. But x final is how far the end of the spring is from equilibrium, whereas y final is how far the ball is from the ground. So
Got it. Okay.
Y final.
Okay, thank you.
This distance is x final. But we can put those together. How should we expect x final and y final to be related to each other?
Would the change in y and x be the same?
From the point where it hits the spring onwards, yes. Because as it compresses the spring, x is increasing and y is decreasing.
Oh, I see. And then, yeah.
What should we expect these distances to add up to?
12.
Sorry, what was that?
Would it be 12?
The spring doesn't stretch all the way up to the top, though.
Oh, so then it would be 3.
Right. Because the spring was originally 3 meters long. If the ball pushes it down some distance x final, and the ball's final height is y final, those two distances have to add up to the original 3 meter length of the spring. So we could write this as...
Sorry, Casey, I got a little lost. Can you kind of backtrack a little and talk about how x and y are related again?
Yeah, x final represents how much the spring has been compressed by the ball by the end. And y final represents the final height of the ball as measured from ground level. Because in this case, we're measuring everything from the ground. We don't have to, by the way. You could set y equals 0 to any location you want. You could say y equals 0 is the location it was dropped from, or maybe you could say y equals 0 is the original height of the spring, or you could say y equals 0 is sea level somewhere deep underground. It doesn't really matter because the important thing is the change in y. But you want to set up a coordinate system. Choose a location to call y equals 0 and stick with it.
Okay.
So if we say ground level is y equals 0, and there's some final height that it gets to, but that final height is some distance x final below the equilibrium point of the spring, then we can say geometrically that the x final distance plus the y final distance, those two distances together make up the original 3 meter length of the spring.
Okay, I see. Thank you.
Any questions on that so far? So then we could write that as a mathematical expression by just saying x final plus y final equals 3 meters. And you got to be very careful about signs here. In this case, y final, would we assume y final is positive or negative?
Negative, because it's decreasing, right?
Well, the fact that y has decreased means delta y is going to be a negative value. But what are we calling y equals 0 here?
Oh, wait.
Yeah, ground level is y equals 0. So if we end up above the ground, then y is going to be what sort of value?
Positive then.
Yeah. So delta y being negative means that the height is decreasing. Y itself being negative means the object is under the 0 mark, in this case, underground. What about x final? Would you treat x final as positive or negative?
Positive?
Yeah, I think I would treat this as positive here. Usually when we compress a spring, we treat x as negative, but that's really just convention. You could say compression is positive and stretching is negative, and you still get the same results anyway. The important thing though is we want to make sure that this equation works. Y final, if we're treating these as distances, distances are positive values. Y final is some positive value. X final is some positive value more than that. We're adding two positives together to get 3. Alternatively, you could treat x final as a negative, but then you'd have to write this as subtraction instead of addition. And I think it's going to be easier to just treat both of those as positive values here.
So if you set 0 to like the middle of between the ground and the ball, like then would that mean everything has to be negative, or?
Like if you said 0 is this location here?
Yeah, like for example.
In that case, the ball's starting height would be positive, but its ending height would be negative.
Okay, and so if you were to set that up with the x final plus y final is equal to 3 meters, you would have to use different values. Would you still get the same? Sorry, I don't really know how to ask, but I'm just wondering like how
you have to change the way this equation is written, because the way this equation is written, the way x final and y final relate to each other depends on how you set up your coordinate system.
Okay.
X, we definitely want to represent distance from equilibrium of the spring. So X, we can't really change the coordinate system, not without changing the way we're writing potential energy. But for Y, there's not really any equilibrium for gravity. I mean, the center of the planet X is equilibrium. We're nowhere near that, so we don't need to worry about that. The important thing is to just choose a height to call Y equals 0 and stick with it throughout the entire problem.
Okay.
Because the important thing is really the change in height, not the height itself. It might make the resulting numbers easier if we choose the equilibrium length of the spring as y equals 0. Because that way we can just use one variable for height and displacement of the spring rather than two variables. But let's go with the coordinate system we've set up so far, where we're treating ground level as y equals 0, just to see how that plays out. If necessary, we might go back and change the coordinate system, but I think we can do it with the coordinate system we have now. That way we can use x final plus y final equals 3 meters and use that as a substitution later on as needed. So we got mg delta y for potential energy of gravity. What's our usual formula for change in spring potential energy?
Half kx squared.
Yeah, 1/2 k times, and since it's a change, I'll write this as delta x squared. And the change in y is negative because the ball is decreasing its height. The change in x squared will be positive because the spring is getting further from equilibrium. So if we start filling in some values, I'm not going to fill in the actual numbers yet, but let's start filling in the deltas at least. M times G times y final minus y initial plus k over 2 times x final squared minus x initial squared. And again, I would usually refrain from filling in the actual numbers until the very end, except if you have some zeros. Filling in zeros can be very convenient. For instance, what values do we know are going to be 0 here?
X initial.
Yeah, x initial is definitely 0. So we may as well fill that in. As for the others, it looks like none of the others are 0. Y final is, we don't know, but x final plus y final has to be 3. And y initial was 12. But let's make this substitution. Notice that if we were to fill in everything we know M, we know G, we know y initial, we know K, we're still missing x final and y final. And we don't want to have one equation with two unknowns. But we don't. We actually have two equations with two unknowns. We've got this equation relating how x final and y final compare to each other. And we also have this equation describing how x final and y final compare to each other. So this is really more like a system of two equations, two unknowns. And what can we now do with this information?
You can solve it in terms of x final or y final and sub it into the other.
Exactly. We can solve for one of those variables in terms of the other. and then substitute that into here.
I have a question.
We could solve for, we could say x final equals 3 meters minus y final, or we could say y final equals 3 meters minus x final, whichever one is more convenient.
Okay.
And
sorry, Tracy, can I ask a question?
Yeah,
so if you have this kind of system where it's like you're dropping a ball onto a spring, does that typically always require some kind of substitution, or is it just in this case?
It sometimes does, sometimes doesn't. It really depends on how you're setting up the coordinate system.
Okay.
In this case, it requires substitution because we have two unknown variables. We don't know how far the ball compresses the spring, and we don't know the final height of the ball.
Okay, thank you.
It's possible, like for instance, if we had instead set up the coordinate system to call this height y equals 0, instead of calling ground level y equals 0, we could have called 3 meters off the ground y equals 0. In that case, y final would just be distance below equilibrium. And so x final and y final would be the same value. So sometimes you can get away with not having to do this just by setting up the coordinate system in a particularly useful way. But the substitution is actually pretty straightforward. All we have to do is solve for isolate one of these variables and replace it with that expression in the other equation. In this case, we could solve for x and plug it in here and then square it, or solve for y and plug it in here. And I think it's going to be easier if we don't have to square the result. So what I'm going to do is solve this for y final. Subtract x final, we get 3 meters minus x final. That means everywhere we see y final, we can just completely replace it with 3 meters minus x final. And if we do that, let's see what we get. M times g, and at this point we may as well start filling in numbers. Usually I would recommend leaving the numbers until the very end, but I think in this case, because of the x squared, it might be easier to fill in the numbers now. What's m times g going to be here?
80.
Yeah, so we've got 80 from 8 times the 10 meters per second squared for gravity. So 80. Y final we can replace with 3 minus x final. And what's y initial?
12.
So minus 12. And k, we're assuming was 400. So k over 2 would be 400, or sorry, 200. And then x final squared, we don't know. But minus 0 at least doesn't change that. So 80 times 3 minus x final minus 12 plus 200 x final squared equals 0. What kind of equation is this? If we've got an x squared and an x and some constants.
Quadratic.
Yeah, this is a quadratic equation. And you can always solve a quadratic equation using either factoring if that's possible, or the quadratic formula, even if it's not factorable easily. So if we can write this in standardized form of something x squared plus something x plus something, then all we need is a quadratic formula. So let's try simplifying that. We've got 200x squared, or x final squared, I should say. For the x final term, we've got a negative x final times 80, so that'll be minus 80x final. And then these constants, 3 minus 12 would be negative 9, times 80 would be negative 720, equals 0. So there's our quadratic. If we can solve that, then we'll have a value for x final. Any questions on that so far?
Can you just repeat the last value in the equation?
The negative 720?
Yeah.
Yeah. From the combining 3 minus 12 to get negative 9, then multiplying that by 80 to get negative 720. And before we plug this into the quadratic formula, it might be useful to reduce a little bit, because I'm noticing, what are all of these coefficients multiples of?
10.
Yeah, they're all multiples of 10. So let's divide both sides by 10. So we get 20x squared minus 8x minus 72. And also those are all, they're all at least multiples of 4, right? 28 and 72. So let's divide both sides by 4 also. 20 over 4 would be 5. 8 over 4 would be 2. 72 over 4 would be 18. So there's our final quadratic. And if that's not easily factorable, we can at least plug it into the quadratic formula to get a solution. Any questions on that so far?
Would you have to use the positive value?
Yes, because the quadratic formula does give you 2 values. We were assuming, and this is why I wanted to be really careful from the start to decide in advance, are we treating x as positive or negative? We are going to get 2 values from the quadratic formula most likely. Presumably it's going to be 1 positive value and 1 negative value. We're going to want to choose the positive value. The negative value you could sort of interpret as if the ball stuck to the spring and started oscillating, the negative value would tell you how high above equilibrium it ends up going in its oscillations. But we don't care about that. We just want to know how close to the ground does it get. So if we plug all this into the quadratic formula, so x is going to equal negative b, which is positive 2, plus or minus square root of b squared minus 4 times a times c, all over 2 times a. And note that this is going to give us 2 values, but we only need the positive value. So instead of having 2 minus some big square root, I'm just going to do 2 plus the square root. So 2 plus square root of, these negatives cancel out, we get 20 times 18, that'll be 360, so 364 divided by 10. I'm pretty sure that's not a perfect square, so I'll just punch that into a calculator. 2 plus square root of 364.
I got 2.11.
Sounds good.
If I plugged it in correctly.
Yeah, I'm getting the same thing. Round it off a little bit, but that should be close enough. So 2.11 meters is x final. And what is that supposed to represent in the physical scenario?
How much the spring is compressed.
Exactly.
Like how far it goes from equilibrium.
Right, the spring gets compressed 2.11 meters down from equilibrium. And what else are we trying to find here? Now that we know how far the spring is compressed, we can also find
Y final.
Yeah, we can just plug this back into our original expression relating those, or even the next level down once we've already isolated y final. Y final is just 3 meters minus the 2.11. So that'll be 0.89 meters. So it ends up 0.89 meters above the ground, having compressed the spring 2.11 meters. So that would be the final situation we're looking for. And again, after that, it's presumably going to bounce back up. Maybe if there's no loss of energy, if it really is a closed system, it's going to bounce all the way back up to 12 meters. But realistically, it's probably going to lose some energy. As the spring compresses and pushes back out again, springs tend to lose energy as they do that. Some of the energy gets converted to thermal energy. But all we really care about is how far does it get compressed. Any questions on that?
Actually, yeah. So suppose we had a situation where it would look like this, and they said that you had a spring that was oscillating, and then you would lose like some amount of energy per oscillation. How would you set up that kind of question? I got stuck on oscillations before, so I don't really know how to approach it.
Well, oscillations just means it's repeating the same cycle over and over again. So for instance, if it hits the spring and sticks to it, we still know it's going to go down 2.11 meters. If you also use the minus and figured out the other solution for x final, that would be how far from equilibrium it goes in the other direction. So it's going to be oscillating between 2.11 meters below 3 and also some distance above 3. In a truly closed system, if it's not losing any energy, it'll just keep oscillating forever. But realistically, it's going to be losing some amount of energy each oscillation. And if it loses energy, what's going to happen to its motion?
It'll go down.
Sorry, what was that?
It'll decrease, like the change in spring mass energy would go down?
Well, I would say the overall total energy decreases. But as it's oscillating, that total energy consists of what types of energy?
Potential gravitational and potential spring mass.
And also, since it's in motion, what else is involved?
Kinetic.
Right. And so if it's losing energy, then the total energy decreases. The total energy available for all three of those decreases. So it's going to end up getting smaller motions because less energy means the oscillations get closer and closer to the new equilibrium. And also less and less speed. It's going to be moving more slowly. So when it first hits, it's going to be doing large oscillation, assuming it hits and sticks. It starts off doing large oscillations, going fast through equilibrium. But as time passes, the oscillations would get smaller and the speed would get slower. If it's losing energy, it's eventually just going to settle down on at rest at equilibrium. But it would be the new equilibrium, not the 3 meters above the ground equilibrium.
Okay, thank you.
Mm-hmm. Any other questions on that situation?
In terms of like going backwards to when we were saying if it was open or not, so the friction would always leave, right? I think I was confused of which direction to draw the arrow, if it was in or out.
In this case, air resistance is acting against the motion. So that would be energy leaving the system.
Okay.
And that's not always true, by the way. You can use air resistance to add energy to a system. For instance, a sailboat. If you've got a boat with this sail here and wind blowing on it, the wind is making the boat get faster and faster. So that is air resistance adding energy to the boat.
Oh, okay.
And even with friction, for instance, if you've got a car driving forward, the wheels are using friction to push the friction with the ground to push the car forward. Or even walking, you're using friction between the bottom of your foot and the ground to propel yourself forward. Without friction, you'd just be sliding in place.
Right.
So friction can be used to add energy to a system. But if you just got like an object sliding, then the friction is making it getting slower and making it get slower and slower. So that would be removing energy from the system.
Okay, thank you.
Mm-hmm. I find a useful general way of thinking about that is to ask yourself, what would you expect to happen in this situation if there wasn't any friction? Like if you're trying to walk, but there's no friction, you're just moving your legs in place. So the lack of friction means you're not getting faster. The presence of friction means you are getting faster. So in that case, friction is adding energy to the system. But if you've got a box sliding on the ground, what would you expect to happen if there was no friction at all?
It would just slide, yeah, like it would just fly across.
Yeah, just keep sliding. The presence of friction then is making it slow down and come to a stop. So in that case, the sliding friction is removing energy from the system. And this is often a very useful approach in any situation, not just with conservation of energy, but also with the study of kinematics, the study of motion we're going to get to in 7b. If you're not sure what friction does in a system or whether friction is playing a role, imagine what would happen if there was no friction. Anything that is missing is something that is caused by friction in the actual situation.
Oh, okay. Thank you.
Mm-hmm. Any other questions on that so far? And so far, we've been looking at this in terms of just comparing the initial situation and the final situation and ignoring what happens in between. But it can be very useful to also look at what happens in between using a graph of energy versus height. So let's try that. Let's try drawing out a graph of these energies versus height and see what that looks like. I think this could lead to some useful insight in the Lennard-Jones potential energy stuff we'll get to as well. But if we just take a look at a graph of height versus energy, and height in this case is going to be between 0 and 12. So we don't need to worry about negative heights here because we're setting 0 at ground level. So height is going to go from 0 to 12. And of course, other important values are going to be 3 meters, and as we found, 2.11 below that, so 0.89. So ball starts at 12, it falls and falls and falls. At 3 meters, it hits the spring, keeps moving down, but gets slower and comes to a stop at 0.89. Meanwhile, if we take a look at energy, to figure out the scale on this graph, how high I should make it, let's figure out how much potential energy it has at the beginning. Because at the beginning, it's only got potential energy of gravity. And how much potential energy of gravity does it have there?
10 meters per second squared.
That's the acceleration of gravity. But remember, potential energy of gravity is m times g times h.
It's 960 kilojoules.
Because we're multiplying 8 as the mass, times 10 as gravity, times 12 as the height. So 8 times 10 times 12 would be 960 joules.
Does this graph show energy or potential energy, or are those interchangeable?
In terms of units, they're interchangeable. So kinetic energy, potential energy of gravity, potential energy of the spring, even E thermal and E bond, they're all measured in joules. So since they're all measuring the same, even though they're different types of energy, they're all energy. They're all measuring the same units, which means you can graph them all on the same axis.
Okay, cool.
This is one of the really convenient things about any two things that have the same units of measurement can be graphed on the same axis, which is a very useful way of comparing them. If they're not measured in the same units, then you can't really do that. And be on the lookout for that, by the way. Anytime you see a graph that's got two different y-axes that are labeled in different units, never trust it. Graphs that are honest always use a consistent system of measurement. But we know, for instance, that 960 is the amount of potential energy it has at that time. So let's mark that at least. 960. We know that when the ball is 12 meters off the ground, it has 960 joules of potential energy of gravity. Do we know what the potential energy of gravity would be anywhere else? Or could we calculate that?
At 0, wouldn't it be, at 0 meters, wouldn't it have 0 energy?
Yeah.
Because
again, we've got mgy. You plug in 0 for y, you get 0 for potential energy. And the ball never actually gets to the ground here, so this isn't really going to be a point in the region where the ball is traveling. It only gets as low as 0.89. But this can still be a useful point for drawing out the graph. And let's throw in a few more data points as well. We could plug in, for instance, 3 and 0.89, because those are really the important values we want to care about. We plug in 3, we get just 8 times 10 times 3, so that'd be 240, which is, I think, a fourth as much. And we could even plug in 0.89. So 0.89 times 10 times 8, 71.2. I'll just run that off to 71. And what shape do these points form?
A linear line.
Yeah, this is definitely linear because mgy is just a constant times the input. In fact, if we fill in that constant, m times g is just 80. So we really are just graphing a line with slope 80.
Is potential energy always going to be linear because of your change in y is not going to be squared?
Right, if we're specifically talking about potential energy of gravity.
Okay, I see.
And also specifically if we're graphing with respect to y. If we were using a different variable as the independent variable, that might not necessarily be true.
Okay.
But in general, anytime you're graphing a function that just looks like output equals a constant times input, that's always going to be a straight line through the origin, and that constant tells you the slope. Any other questions on that so far? And do we have any other types of energy we want to graph here?
Spring mass?
Yeah, we definitely want to graph and in this case, I would just call it the spring potential energy, because we're not really including the mass. We're taking care of that with the gravitational potential energy. The spring here, we really are just treating the spring as an independent object. So we've got the spring potential energy, and where's the equilibrium for the spring here?
3?
Yeah. So the spring is going to have 0 potential energy at 3. So instead of, I mean, we usually expect spring potential energy to be what shape on the graph?
Parabola.
Yeah. 1/2 kx squared is going to be a parabola, specifically a parabola centered at the origin. But instead of centering it at the origin, we're shifting it to be centered at 3 because we're graphing y instead of x.
How do you know that it's still parabolic given that it's not being graphed in terms of its indicator?
Good question, because that is something you always want to be careful about. You should only trust what the equation says about what the graph would look like if that variable is the independent axis. But if you take a look at how those are related, x final plus y final equals 3, or in general, x plus y equals 3. If you actually fill that in, if you replace x with, in this case, you'd subtract subtract y from both sides. So replace x with 3 minus y. 1/2 times k times 3 minus y squared is still going to be a parabola. It's just centered at y equals 3 instead of at x equals 0. All we're doing here is a change in coordinate systems. So, in fact, you could even reverse the order here, because since this is squared, the order of subtraction doesn't matter. So we could just write this as k over 2 times y minus 3 squared. And if you go back to graphing theory from high school algebra, if you take a function and subtract something from the input before you apply the function, all that does is just take the shape and shift it in the direction of the input variable. So all the minus 3 does is shift the graph 3 meters to the right. Technically 3 meters up. It's just that we're treating the up axis as the horizontal axis. So we shift it 3 meters along the y-axis, and the k over 2 just controls the steepness of the graph. So we're going to get a parabola centered at 3. However, the spring doesn't start interacting until what happens?
The ball applies a force to it.
Right. And that's not going to happen until the ball actually hits 3 meters. So instead of drawing out a complete parabola here, we're going to skip the higher y value side, the right side, because the ball hasn't hit the spring yet. We're just going to include the side where it's actually hit the spring. Also, what's one other location where we can figure out the spring potential energy? What's the one other location we actually care about?
At 0.
At 0? We could fill in k and 0 for y, but the thing is the ball never actually reaches 0. Would
it be the final x position?
Yeah, the final, or I would say the final y position in this case, because we know it does reach a final x value of 2.11, but it reaches a final y value of 0.89. And we were assuming that, where did all that spring potential energy come from?
Dropping the ball?
Right. We dropped the ball. We started with the ball having lots of what type of energy?
It had a lot of potential energy initially.
Right. And specifically, what type of potential energy?
Gravitational.
Yeah. It starts with lots of gravitational potential energy. It loses most of that, turning into spring potential energy. So we can use conservation of energy to figure out how much spring potential energy there is at 0.89.
Do you have to factor in kinetic energy now that we're not looking at just the final and initial positions?
We would in between, but if we look at just 12 and just 0.89 for now, what do we know about the kinetic energy at y equals 12 and the kinetic energy at y equals 0.89?
The kinetic energy would be 0 at both.
So we can at least fill that in. We can say kinetic energy at 12 is 0 because we've just dropped it. Kinetic energy at 0.89 is 0 because we found that's where it comes to a stop. And of course, it's going to have other values in between. But these are some very useful values to use because we can now say, oh, also to fill in the potential energy of the spring graph, before the ball hits the spring is not stretched out yet. So the spring's potential energy is 0 until the ball actually hits it. Then it starts curving upwards. So since the ball hasn't hit the spring yet, the spring is 0 potential energy until the ball actually reaches 3 meters and hits the spring. And that means there is now one location where we know all the types of energy. We know we've got 960 joules of potential energy of gravity, no spring potential energy because the ball hasn't hit the spring yet, no kinetic energy because we've just dropped the ball. So at that location, what is the total energy?
960.
Right, we've got 960 joules of total energy. And in a closed system, what do we know?
Energy is conserved.
Right, so the total energy stays 960 as the ball falls. We know E total is 960 the whole time. And since we know that the gravitational potential energy is 71 and the kinetic energy is 0 at this location, we can just deduct that from 960 to find the spring potential energy. Because those values, 0 plus 71 plus something, have to add up to 960.
I have a follow-up question about potential energy of the spring. So I understand why it's 0 between 3 and 12, but then between like 0 and 3, you can't draw as like a parabola, that one segment?
It is definitely going to be a parabola from the 1/2 k times something squared. What we just need to do is figure out how high that parabola goes. Because before we draw that in, I want to know how high is it going to go so we can be accurate about it.
Okay. And it's still a parabola even though it's in terms of y?
Yes, and the reason for that is because we've got a linear relationship between x and y. If we had had some different relationship between x and y, like if we had had, I don't know, x final plus sine of y final or square root of y final or something, then that would be different. But the fact that the only difference between x and y is they add up to a constant, that means that the result, if you replace x with 3 minus y, you still get a parabola.
Oh, that's what
The
you're
only
saying.
thing it does is shift the parabola. In fact, I wouldn't really even say it's shifting the parabola. We've got the same parabola, but we're using a different coordinate system to draw it.
Okay.
So
Okay.
it's not even so much shifting the parabola. It's you've got the parabola, you've got a coordinate system, you're shifting the coordinate system while keeping the parabola where it is.
Gotcha. Okay.
So if you subtract the 71 from 960, that's what, 889? So that would be the spring potential energy at that location. And with those points, and of course you could fill in more values if you needed to, but I think this would be enough to sketch in a pretty good rest of the parabola. Something like that. And let's go ahead and finish this off by drawing in the kinetic energy graph as well. We've got 2 locations marked already. We know the kinetic energy is 0 at 12 and also 0 at 0.89, where it starts, where it comes to a stop. The other important value we should really be looking for is at y equals 3. Because at y equals 3, we know we've got no spring potential energy yet because the ball has just hit the spring, hasn't compressed it yet. And we know the potential energy of gravity calculated earlier is 240 joules. So if we really just deduct 0 and 240 from 960, we get the kinetic energy. 960 minus 240 is 720. So we can say that at the location where the ball hits the spring, the kinetic energy is 720. From 12 to 3, we've just got potential energy of gravity decreasing linearly. So we should expect kinetic energy of gravity to be increasing linearly at the same rate, because a decrease in potential energy in this case is matched by a corresponding increase in kinetic energy. So this should just be linear. So there's that portion of the kinetic energy graph. Afterwards, though, the ball hits the spring. Note that potential energy of gravity is still decreasing, but potential energy of the spring starts increasing, slowly at first, but then faster and faster. So the kinetic energy is going to have to overall decrease to get down to 0 by the time we get to 0.89. Just past 3, we've got a small increase in spring potential energy, but a faster decrease in potential energy of gravity. So overall potential energy is still decreasing, so kinetic energy is still increasing. But past a certain point, spring potential energy is increasing faster than gravitational is decreasing. So overall potential energy is increasing, meaning kinetic energy curves back down to a decrease, getting faster and faster. Essentially a parabola, but not quite the same parabola as spring potential energy, because it has to balance out spring potential energy and gravitational potential energy. And if you add a quadratic function plus a linear function, you get another quadratic function. So this is going to be a portion of a parabola. It just has a vertex at this weird location a little below 3. And it hits 0 at 0.89 because at 0.89, the ball comes to a stop. So that's the full graph. We've got our spring potential energy graph only kicking in once the ball actually starts compressing the spring. We've got a gravitational potential energy graph, which we can really ignore after 0.89 meters because the ball doesn't actually get past that. And we've got our kinetic energy graph. Ball's getting faster and faster and faster as it falls, then rapidly slows down and comes to a stop after it hits the spring. So that's the complete graph. See you next time.